Welcome to the second number theory lecture on the topic of divisibility. Most of the problems in this lecture are based on problems from the book 250 Problems in Elementary Number Theory by Sierpinski. And you can borrow this from the Internet Archive. I have the link here. You can also purchase this. It's still available on Amazon, even though it was initially published in 1970. So our first problem is prove that 13 divides exactly 2 to the 70th plus 3 to the 70th power. And the hint is to make use of Fermat's little theorem. We saw this in our previous lecture, the first lecture on divisibility, and we'll use it here again to solve this problem. So if you want to give it a try, just hit the pause on the video, and then I'll come back and continue with the solution on the next slide. We can divide the problem into two pieces. First, we'll look at the remainder of 2 to the 70th power divided by 13, and then we'll look at the remainder of 3 to the 70th divided by 13, and then add the two remainders, which we hope to be 0, in order to prove our result. So we'll use Fermat's little theorem twice here. First, we'll use it on 2. So we have let a equal 2 and p equal 13. And that gives us 2 to the 12th is congruent to 1 mod 13. Then we can raise both sides of this to the power 5. We get 2 to the 60th, and then 1 to the 5th, of course, is 1. But we need 2 to the 70th, so we need to compute 2 to the 10th. That's 1024, and we can write that as 78 times 13, which is 1014 plus 10. But this part here, mod 13, is 0, and so we just get 10 mod 13, but we can write that also as minus 3 mod 13. And so 2 to the 70th is this result times this result here. So it's 1 times minus 3, congruent to minus 3 mod 13. And you'll see in a minute why I wanted to use minus 3 here. Then we go to the 3, and we use Fermat's little theorem again, but this time A is 3, and our prime P is again 13. So we get 3 to the 12th is congruent to 1 mod 13. We take both sides of this to the 5th power, and we get 3 to the 60th equals 1 mod 13. So we still need 3 to the 10th power. I'll break that into two pieces. First, we'll do 3 to the 5th, which is 243, which is 234 plus 9. The significance of this is it's 18 times 13, so mod 13, this is 0. So we just get 9 mod 13. Then we need to square this again. And so we get 3 to the 10th equals 9 squared is 81. But 13 times 6 is 78. And so that leaves a remainder of 3. You can see now why I wanted to use minus 3 here. So 3 to the 70th is this result times this result here. So we get 1 times 3. So 3 to the 70th is congruent to 3 mod 13. And then we just add this, and we see that it's congruent to 0 mod 13, which implies, or is equivalent to 13 dividing 2 to the 70th plus 3 to the 70th exactly. Our next problem is to show that 11 times 31 times 61 divides 20 to the 15th power minus 1. I'm going to show you a hint on this slide, so if you don't want to see the hint and just want to try the problem as it is here, you may want to pause. Okay, so let's look at the hint. The hint is to apply Fermat's little theorem to 11 and 61, and then for 31, Note that 20 to the third power is 8,000, which equals 258 times 31 plus 2. So 20 to the third power is congruent to 2 mod 31. Okay, so that's the hint. And if you want to pause here and give the problem a try, that would be great. And then I'll give you the solution on the following slide. In terms of modular arithmetic, the equivalent problem is to show that 20 to the 15th minus 1 is congruent to 0 mod 11 times 31 times 61. And since 1131 and 61 are prime, that means we can show that each one individually divides 20 to the 15th minus 1 without any remainder. So that's what we'll do. We'll start with 11. And we make note that 20 is congruent to 9 or congruent to minus 2 mod 11. And then we can apply Fermat's little theorem with P equals 11 and A equals minus 2. And we get this result here. But that's the same as 20 to the 10th. We can just substitute in minus 2 for 20. So we have 20 to the 10th is congruent to 1 mod 11. We still need to get this up to 20 to the 15th. So we notice that 20 to the 5th, substituting in minus 2 for 20 because of this relationship here, is congruent to minus 2 to the 5th, which is congruent to minus 32, which is congruent to 1, since 3 times 11 is 33, and that makes, and we add that to the minus 32, and we just get 1. So then if we multiply this result times this result, we get 20 to the 15th, and then we subtract 1 from it. So we get 1 times 1 minus 1, so that's 0. And that's congruent to 0 mod 11. So that's what we want for the for 11. And then we go to 31. Using our hint from the previous slide, we have 20 to the third is 8,000, which is 258 times 31 plus 2. But mod 31, this term is 0, so we just get congruent to mod 2. Then we can write 20 to the 15th is 20 cubed to the 5th. Then we plug in 2 for 20 cubed. So we get 2 to the 5th. That's 32, which is congruent to 1 mod 31, or the same as 20 to the 15th minus 1 being congruent to 0 mod 31. So that checks off the second one. Then the third one is a little bit more tricky. We note that 3 to the 4th equals 81. And so that means that 3 to the 4th is congruent to 20 mod 61. That's the remainder of 81 mod 61. So we have 20 to the 15th, and we plug in 3 to the 4th for 20, since they're congruent. And that gives us 3 to the 60th mod 61. But we know that that's congruent to 1 mod 61 by Fermat's little theorem. We just have P equals 61 and A equals 3. And so we have 20 to the 15th is congruent to 1 mod 61, or 20 to the 15th minus 1 is congruent to 0 mod 61. So we've shown each term here, 11, 31, and 61, satisfy these three congruences here. So we have 20 to the 15th minus 1 is congruent to 0 mod 11, which we showed here, and then similarly for the 31 and 61. And so the product, since these are prime, the product here, mod the 20 to the 15th minus 1 is congruent to 0 mod the product of 11, 31, and 61, which is what we wanted to illustrate. For our next problem, we want to prove that for m being a natural number and a greater than 1, a is also an integer, that the greatest common divisor, which we use this notation here, these parentheses, a to the m minus 1 divided by a minus 1, comma, a minus 1. So the greatest common divisor of these two quantities is equal to the greatest common divisor of a minus 1 and m. And if you want a hint, I'll show you in a second. If you don't want a hint, then you may want to pause and try the problem from here. Okay, so here's the hint. There's something called the Euclidean algorithm. We'll see this in some of the other problems. And there's different ways of expressing this. The way I'll express it for this particular problem is as follows. The greatest common divisor of x and y is equivalent to or equal to the greatest common divisor of x mod y, comma y, so these two numbers, or that's the same as the greatest common divisor of x plus some integer times y and y. So I have an example here. The GCD, greatest common divisor of 49 and 21, is the same as the greatest common divisor of 49 mod 21 and 21. And then this here is if you take 2 times 21, you get 42, and that's 7. And so that's equivalent to the greatest common divisor of 7 and 21, which is 7. We could have probably seen that just from looking at it here, but I wanted to illustrate this equivalence here. Okay, so that's the hint for solving this or proving this result, and I'll show you how to do that in the next slide. We have the geometric series here, which equals one of the terms in our GCD that we're trying to evaluate. So we'll let S equal this, and this is the geometric series. And so what we want to do is find S, the GCD of S in a minus 1. First we'll reduce S modulo a minus 1. We note that a is congruent to 1 mod a minus 1. And then we can raise both sides of this to the n power, and we get a to the n is congruent to 1 to the n is congruent to 1 mod a minus 1. And that's true for n greater than equal to 0, n being an integer. We only need to go up to m minus 1 here. So S mod a minus 1 is 1 plus 1 plus 1 plus 1. So there's m terms here. So S is congruent to m mod a minus 1. Or to write this differently, this is the same as saying S equals m plus a minus 1 times k for some integer k. Then we just plug that into the formula we're trying to solve. So the GCD of S comma a minus 1, plug this in for S, so this is equal to this here. And then we use our Euclidean algorithm to get from here to here. You notice we have an a minus 1 in here and an a minus 1 times k on this side. So this is the same as m. The GCD of m was a minus 1. And therefore, just looking at the two sides of this, S is a to the m minus 1 divided by a minus 1, a minus 1. Then the order doesn't matter here. The GCD is the same. So you have this here, and that's what we wanted to prove. For the next problem, we're asked to prove that 3 times the, let me point to it, 3 times this sum here, 1 to the 5th, 2 to the 5th, up to n to the 5th, is divisible by 1 cubed plus 2 cubed, all the way up to n cubed, for every n being a natural number, so for every positive whole number. So you may want to give that a try. I'm going to give you a hint on this slide, so if you don't want to see the hint, you may want to pause right here and give the problem a try. If you want to see the hint, I'll show it to you in a second. Okay, so here's the hint. This pretty much gives it away. If you go on the internet and look up the formulas for the sum of cubed, numbers cubed, whole numbers cubed, and there's also a formula for the sum of numbers raised to the 5th power, and that pretty much gives you most of what you need to solve the problem. Okay, so I'll give you the rest of the solution on the next slide. I restated the problem here at the top. We want to show that this sum always divides this sum here, multiplied by 3 for any n being a natural number. Then this was the hint that I mentioned on the last slide. You can look these up. I found the formulas on Wolfram Math World, but I'm sure you can find them in other places. So this is the formula for k cubed from k equals 1 to n. And then the formula for k to the 5th is this here, and then we want to multiply by 3 because we want to show this is divisible into this, where you multiply this by this term here by 3. So it's 3 times 1/12 times this here. And you can see why the problem had a 3 in it, because the 1/4 cancel out. And then you just want to divide this into this using long division. And it turns out, if you go through the details, that this equals this expression here times this here, and so these are both integers. So we've proven that you have divisibility. In terms of long division, if you're not familiar with this, my first lecture on divisibility, the one just before this, I went through an example of doing long division of polynomials. I didn't give the details here, but as I say, you can, if you want to see an example, I have one in my first video on divisibility. Our next problem is to determine all n greater than 1 such that n divides this sum here, 1 to the n plus 2 to the n plus n minus 1, all the way up to, I should say, n minus 1 to the n. So this is not an easy problem. It actually took me 3 slides to present the solution, which I'll show you. If you're interested in a hint, I'll show you the hint on this slide. If you're not interested in a hint, then just pause here and try solving the problem from this point. Okay, so here's the first hint. And this is probably a general advice that I would give if you have a problem like this and you're not sure where to start. It's usually a good idea to maybe just compute a few of the numbers for n equals, well, we're told n is greater than 1. And I should have said n is a natural number. That's usually the case. Most of these problems, either the variables are natural numbers, in other words, positive whole numbers, or in some cases they're integers, which could be either positive or negative whole numbers, as well as 0. So in this case here, we're talking just about positive whole numbers, and we're starting with 2. And if you do the computation for 2, we get 1, so that doesn't work. 2 doesn't divide 1 even exactly, but if you put in 3, you'll get 9 for this expression, which I'm calling s sub n. So that works. And you put in 4, and 4 divides 100 evenly, but not 98, so that doesn't work. 5 works. You get 1300 for this expression. 6 does not work, but 7 does work. This is a rather large number, but if you check it on your calculator, you'll see 7 exactly divides this number. So it looks like, and it's not a proof, but it looks like maybe the odd numbers work and the even numbers don't work. And in fact, that's the case. So that's the hint I'll give you. That's a good starting point. But if you didn't know that, that would make the problem even harder. Then there's another hint that you may want to use. This is similar to Fermat's little theorem, except instead of having the prime number, remember we had a prime number here and in the exponent, there's something called Euler's totient function, which is this thing here, phi of n, and the a, which is an integer raised to the phi of n, is congruent to 1 mod n. Now I need to tell you what the totient function is. It counts the positive integers up to a given integer n that are relatively prime to n. So if you have a prime number, then the integers relatively prime to a prime number p would be 1 to all the way up to p minus 1. In other words, it would be p minus 1. So this, for n equals a prime number, this it reverts back to the Fermat's little theorem, but it's more general because you can do it for any n. It doesn't need to be a prime number. Okay, so that's those are the two hints, and if you want to pause here, I'll give you the solution in the next 3 slides. So as I say, it's not an easy problem. Even with these hints, it's still not an easy problem. I copied our problem from the previous slide. I have it here at the top for our reference. And I used the notation S sub n equals this sum. We want to show that n divides S sub n, or at least we want to find what values of n when this is true. And from our analysis on the previous slide, we had some reason to think that maybe for n being odd, we have a divisibility. In fact, we're going to look at that on this slide here. So let n be an odd integer greater than 1, and consider any one of these terms, n minus k to the n. So, for example, if we take k equals n minus 1, we get this term. If we take k equals 1, we get this last term, and then everything, we get any of the terms in between. So we're basically going from k equals n minus 1 to 1 to get each one of these terms. So this is a general term in this summation, and we can use the binomial expansion, which I've written out here. So you have n choose 0, which is just 1, times n to the n, minus n choose 1, times n to the n minus 1, and then k to the 1. And then the next one would be, I didn't draw it in here, would be n choose 2, then n to the n minus 2, k to the squared. So the powers of n go down, the powers of k go up, and you continue all the way down to the last term here, where you just have a power of k. So if we take this mod n, this term has an n in it, and all these terms have an n in it, and so they would all be 0 mod n except for this last term here. So when we do that, we have n minus k to the n is congruent to minus k to the n, which is congruent to minus 1 to the n, k to the n mod n, but n is odd, so minus 1 to the n is just minus 1, and that means that n minus k to the n is congruent to minus k to the n mod n. So let's continue. We want to pair our terms in this sum, keeping in mind there's an even number of these because n is odd, and so this last term here would be an even. Excuse me. So we pair the first one with the last one, the second one from the second from last, and in general we pair terms like this here, k ranging from 1 to n over n minus 1 over 2. And when we take this mod n, the first term is just kn mod n, and the second term, this here, we've just showed that it's minus k to the n. So we get 0 for this sum here, mod n. And if we take the sum from k equals 1 to n minus 1 over 2, we'll catch every one of the terms here as we pair them off, and we're just going to get the sum of 0, n minus 1 over 2 times, and that's congruent to 0 mod n. So if S sub n is congruent to 0 mod n, that means that n exactly divides S sub n, which is what we wanted to show here. So for n equals an odd number greater than 1, we do have divisibility. On the next slide, we'll look at the case for n equals even. Let's look at the other case where n is even. In this case, it turns out that n does not divide S sub n. Since we're assuming n is an even number, we can factor out the highest power of 2 and write n equals 2 to the k times m, where m is odd and k is greater than or equal to 1. To prove that n does not divide the sum s sub n it is sufficient to prove that 2 to the k does not divide s sub n. So that's what we want to do. So we want to analyze the sum s sub n equals, recall we defined it as this, mod 2 to the k, and we'll analyze this by splitting it into two cases, where you have even basis for one case and odd basis for the other case. And the basis here, even basis, are 2 to the n, 4 to the n, and so on. Then the odd basis are 1 to the n, 3 to the n. So the basis is referring to the number raised to the power, not the exponent. So we'll look at the even bases first. Let j be even, so that'll take into account the 2 to the n, 4 to the n, and so on, which means we can write j as in the form 2r, where r is a positive integer, and then j to the n, we just plug in 2r for j, and we get this. Then this is equal to 2 to the n, r to the n, and we want to show that j to the n is congruent to 0 mod 2 to the k. And to do that, it suffices to show that 2 to the k divides 2 to the n. In other words, you can divide out a 2 to the k from here, and in which case that would imply j to the n is congruent to 0 mod 2 to the k. So in order to show this, this requires that n is greater than or equal to k. Since n is a multiple of 2 to the k, that's what we defined up here, we have n is greater than or equal to 2 to the k. And because 2 to the k is greater than or equal to k for all integers k greater than or equal to 1, it follows that n is greater than or equal to k, our condition here. Thus, j to the n is congruent to 0 mod 2 to the k. Okay, then let's look at the case where we have odd bases. Let j be odd, and thus relatively prime, the 2 to the k. Right, an odd number cannot share any factors with 2 to the k, otherwise it would be even. So this is where we use Euler's theorem. But first we need to compute what is phi of 2 to the k is. And we do that by, remember, phi is the number of integers less than or positive integers less than or equal to 2 to the k in this case, but relatively prime with 2 to the k. So there's 2 to the k positive integers less than or equal to 2 to the k. That's pretty simple. And then the ones that are not relatively prime is basically the even one, so it's half of 2 to the k. So this number here, and if we subtract the 2, we get the number of positive integers that are relatively prime to 2 to the k. So that's what this is here. Then we can factor out a 2 to the k minus 1, and we get 2 minus 1, which is just 1, of course. So we get 2 to the k minus 1. And that's what we need to plug into Euler's theorem. So we have j to the phi of 2 to the k, and that's j to the 2 to the k minus 1, and that's congruent to 1 mod 2 to the k from Euler's theorem. Since n is a multiple of 2 to the k, it is also a multiple of 2 to the k minus 1. So let's say n equals some integer times 2 to the k minus 1. Therefore, we can write j to the n equals j to q times 2 to the k minus 1. And we can just write it this way here, j to the 2 to the k minus 1 to the q power. And then we know this inside of the brackets is 1, so we get 1 congruent to 1 mod 1 to the q, and then congruent, and this is just 1, of course, so it's congruent to 1 mod 2 to the k. So this confirms that every odd term is congruent to 1. So each of the 1 to the n, 3 to the n, and so forth are congruent to 1 mod 2 to the k. So we're not done yet. We need to just put together the different pieces. We have And for the even basis, j to the n is congruent to 0, mod 2 to the k. And for the odd basis, we have j to the n is congruent to 1 mod 2 to the k. So it's just a matter of putting these together. I'll do that on the next slide. Okay, so just putting the pieces together. The even terms contribute 0, and the odd terms contribute 1. That's what I just said at the end of the last slide. The number of odd integers less than n is exactly n over 2. This is because we assumed n was even. And so we have s sub n. We don't need to add in the even terms at all. There is 0. But the number of odd terms is n over 2. So we have just summing 1 n over 2 times, we get n over 2. So s sub n is congruent to n over 2 mod 2 to the k. So for s sub n to be divisible by n, in the case that we assumed the n was even, it must be divisible by 2 to the k, which would require n over 2 to be congruent to 0 mod 2 to the k. That's just from our analysis up here. So substituting n, remember this is how we broke n up at the very beginning of the previous slide. We substitute that in for n here, n over 2. We get this here, which equals 2 to the k minus 1 times m. And for 2 to the k minus 1 times m to be divisible by 2 to the k, m would have to be even. Right? We would need to draw out another 2 out of the m. But we define the m as an odd part of n. Thus we have a contradiction, and therefore n cannot divide the sum when n is even. Okay, so just to summarize, we have a solution to our problem when for any positive integer n being odd, and whenever n is even, we do not have a solution to our problem, which was divisibility of n into our sum here, s sub n. Okay, so that was the last problem in this lecture, and I have several more coming, so stay tuned. And if you like this, please click the like button. That helps me in terms of my presence on YouTube.